Okay, students, now in the last video lecture we talked about the essential thermodynamic requirements of chemographic analysis, which is understanding phase relations, intersection tie lines, composition space. There are a lot of many other aspects, but for the moment, to understand graphically how phase relations can be seen in complex system, and we try to see finally that we don't distort the variance of the assemblage, and so there are certain rules, and these rules guide you to to reduce the chemical components that make up that particular assemblage into from a very large number to some sort of sizable number, and by bringing in the rules 1, 2, 3, 4 and trying to minimize it to a smaller composition space. But beyond that, rule 1, 2, 3, 4, beyond that you can't progress. So then you have to take what I explained as projections. So you take a mineral, you take a plane, you take a mineral from where you are going to project, and the other minerals are somewhere between the screen and this mineral, and then you project them onto a particular plane. Last time we projected on AFM plots for mica schist or metapelites, as you have seen. But sometimes what happens that you start with a system, you start with a component, and then maybe you reduce it, but still the components are high. So you have to reduce it still further so that it's manageable. So rule 1 to 4 is about thermodynamics. Rule 5 is how you project. And that rule 5 you can go on repeating if possible. In all assemblages it's not possible. It's also possible in specific assemblages, specific choices of minerals, etc. Now yesterday we did the AFM projection for mica schist, but remember we were talking about metamorphic rocks. So today I take up a topic where you do repeated projections. I will not talk about, this is from a paper by Spear, a very famous person. Spear, I think 1981, 82, something like that. And the paper is on an area is post-pond metavolcanics. And it was published in Journal of Petrology. So that's quite an old paper, 40 years ago, and it still is taken as a wonderful paper to do repeated projections. So you can type out Spear post-pond volcanics Journal of Petrology and you will get only one reference. This is essentially post-pond volcanics is from Vermont in USA. So he suggested a magnificent projection which has been used by several people, including myself, and we got very good results from it. A very good projection, very intelligently done, and that I would like to show you. In fact, if you want, I can send you the PDF uploaded in the Google Classroom. It's really worth reading it, but it's a very long paper and fundamentally involves a lot of complications. So much of it you will not understand at the present level. But some parts, after I derive this, I will upload it so you can see the graphical analysis part, but the thermometry part also you should be able to understand. But they involve mafic rocks and they involve amphiboles and they are very complicated, right? But it will, first if I had given you the paper before the lecture, you wouldn't understand a head or tail out of it. But after this metamorphic phase equilibrium lecture, I think you will understand about 50% of it. Right. Okay, so in what is post-pond volcanics? There are in this assemblage, it involves different minerals, but it involves a plagioclase and it involves hornblende. These are the two phases that are there. The other phases, whatever are there, cummingtonite, michicite, all these phases, they are different. What we do is, there is plagioclase and this is hornblende. And what he does is, project the mineral analysis first from plagioclase and then from hornblende. So initially he had a log system which he reduces to Na, Ca, Al, Fe and Mg. This was the original system. Using rule 1 to 4, he brought down a 15 component system to essentially a 5 component system. And then you see it is 5 component and still it can't be presented on a book. So what he did was he first eliminated sodium, that means he was projecting from a sodic phase, and then he projected from, so when he projected from sodium, sodium was no more there, but they had calcium, aluminium prime, iron prime, and magnesium prime. These were the compounds. And he did this by projecting from plagioclase, which composition was anorthite 35, was it?
Yes.
Anorthite 35. This was the projection point. So from this assemblages in this composition space, he used plagioclase. He did this projection. So what he did was from NaCalFeMg, he now came down to Ca prime, Al prime, Fe prime, and Mg prime. And then he took Hornblende again, and I will give you the composition. It is Na 0.5, Ca 1.70 or 75?
1.7.
Na 1,
So
Ca 1.7,
Mg.
Fe
85.
1.85. Both are 1.85?
Yes.
1.85. Aluminium 1.4.
Again aluminium.
Aluminium 1.5. And silicon 6.5. And O22, O is O twice. So that was the Hornblende rock. And here you can see these are the different sites. A site. This one is the octahedral site. This one is the tetrahedral site. So he had a plagioclase of this composition. He had a Hornblende of this composition. And taking the Hornblende and eliminating Ca prime, he found out a scheme by which he could project the minerals on Al, Mg, Fe composition space. So essentially it involves 1 and then 2 cycle projections. But you can well understand, I will do the derivation. So he took a 5 component system, which was already an approximation from 50 components. Then he takes plagioclase and eliminates sodium, so he gets a 4 component system, and still it's a tetrahedron, and still it's difficult to see. Then he takes the Hornblende, which is present in all the phases. Remember, from rule 5, it should be present in all phases. So this plagioclase and this Hornblende of this composition is present in all phases. And so he takes this and then eliminates calcium prime to get Al double prime, Mg double prime, Fe double prime. Right? So we will see so in the first one, this is the minerals that fall in this composition, this is his source, and this is his screen on which he projects all assemblages. So he has all minerals in this assemblages, but he takes this as a source, same like muscovite that I did for AFA projection, and then plot it on the Ca prime, Al prime, Fe prime, Mg prime space. That is equivalent to your AFM plane of the projection. But there it was a plane, here it's a tetrahedron, it's a space. And then he takes this and does this on a plane. Now, how does he does this? how does he take plagioclase anorthite 35 and he projects it? That's the point. So what he does is, if you say that there is plagioclase and its composition is AM35, that means essentially what you mean NaAlSi3O8. This is equal to 0.65 and 0.35 is CaAl2Si2O8. That is what you mean essentially for your plagioclase. So now, you see both of them add up to 1. So the total now comes to, if I take this, then Na 0.65, Ca 0.35. Okay? Then you have aluminium. I will give you the value. I calculated it. You can check it out. Aluminium comes to as 1.35 and therefore silicon comes to as 2.65. The total is 4 here, the total is 5 here, and 0.8. So this is your composition of the plagioclase, which you call AM35. So if you take a plagioclase AM35 and you take 0.65, which is albite, 0.35 is AM35, Cl2Si2O8, and I multiply all of this into 0.65 and all of this into 0.25, so I will have Na 0.65, Ca 0.35, this total add up to 1. And this 1.35 and 2.65, this adds up to 4, and then 0.8. That's the composition of the plagioclase. So now, if I have to eliminate sodium, so you see what happens here. So, here you see 0.65 sodium is equal to
0.350.
I think I'm writing the wrong way. This value is 0.538. Right? 0.538. See, if I have to remove sodium for 0.65 sodium here, so much calcium needs to be removed, because that is your projected from plagioclase. So 0.65 of sodium is 0.35 of calcium. So for every sodium that you remove from every other elements, it's 0.35 by 0.65, that is 0.35. That means your Ca prime then will be equal to the actual Ca minus 0.538 Na. Have you understood? That is important. What is your Ca prime? The original Ca prime in a mineral. But that is not all. Because of projection and elimination from sodium, this much amount of calcium has to be removed. This is actually calcium, but this is sodium equivalent of that calcium. So your Ca prime becomes equal to Ca minus 0.538. So let's say if we take aluminium, what happens? So here you see your aluminium, your sodium again 0.6, if you remove sodium, 0.65 sodium is equivalent to 1.35 aluminium, yes or no? Because it's 1.35. If I do this, then one sodium is unitary method of the olden times. So it's 1.35 divided by 0.65 aluminium, which is equivalent to 2.077. this value. So now if I take aluminium prime and project another mineral, therefore I will have aluminium minus 2.077 sodium. So if you are projecting from plagioclase of this composition, then calcium prime in the new composition space in which you are projecting it should be equal to the Ca prime in this system minus 0.538 sodium, which is the equivalent amount of calcium that needs to be removed. Similarly for aluminium. But here there is no iron or magnesium. So if you remove sodium, no change in iron will be there. So what will happen? Your Fe prime will be equal to Fe because there is no iron. And your Mg prime will remain Mg. So this is exactly what happens. So if you transfer from this 5-component system to the 4-component space by projecting from plagioclase, then in the new space, the plotting, these are called the plotting coordinates. The plotting coordinate should be this. These are the plotting coordinates. If you have to plot any mineral, then you have to subtract this to form your new mineral. So your new mineral will not have the composition with which you are accustomed to. It will never be, because you have corrected it for the projections. Your mineral, the mineralogy that you knew, your garnet will not look like garnet anymore. That is important, because you are correcting the components that make up the garnet. So if you do that, just for the sake of it, I'm projecting from here, so I know the coordinates, so I will just write it, plagioclase, anorthite 35. Then this is the plotting coordinate. Let's see what happens to the hornblende already. Because you see, let's see what happens to this hornblende. This is an hornblende. But you are already projecting it from plagioclase. So the hornblende composition that you show here will not be hornblende anymore. What? So what will happen? In that new hornblende, I will write this. In the new hornblende, there will be no sodium, because sodium is extracted out of the system. So your sodium will turn out to be blank. There is no sodium because you have converted to sodium. What should be calcium? You can see what should be the value for calcium. It should be 1.7, no, 1.7, 1.7. What will be the value? Let me write it here. Calcium would be equal to, the total value is 1.7. 1.7 minus 0.538 into 0.5. Do you see that? This, for this removal of this sodium, this calcium 1.7 loses a part of calcium, because that is what is lost when you're projecting with plagioclase. And this value now comes to as equal to 1.43. So your calcium now becomes 1.43. According to my calculations, yes, it's 1.43. So, sodium has become blank, your calcium has become 1.43. This new hormone, it was 1.7. But this amount has been removed because of 0.5 sodium. Now let's see, if we go to Fe, 1.85 remains 1.85 because in plagioclase there is no iron removed. So what happens is, your Fe remains 1.85, your magnesium remains 1.85, and what I did was, I clubbed the total amount of aluminium. I clubbed the total amount of aluminium, which is 2.9 here. So what will be the new aluminium value? I think I should write Ca prime, Fe prime, Mg prime. Now I have Al prime. What is Al prime now? Al prime is 2.9 here, 2.9 minus 2.077 into 0.5 for this one. So this value comes to as 1.862. This value comes to as 1.862. So instead of 2.9, now my Hornblende aluminium prime would be, instead of 2.9, it should be 1.862. So you see, since you have already projected it from plagioclase, your Hornblende is also projected into this composition space. In this composition space, your new Hornblende has this composition. Rest does not matter to me. Rest does not matter to me. But this is what the compositions are. But now, what we do is, our next step was, remember, I think we started with this component, if you remember. Then we went to this component where we are. And finally, Spear suggested that we can do it this way by using the Hornblende composition. Now you can see what will happen. You will write Al double prime. You're removing now calcium. If you're removing calcium, some of the iron will go, some of the magnesium will go, and some of the aluminium prime will go. So now what we do, we have to find out the coordinates first. So what will be your Fe prime? Okay, let me see. I don't know whether I can fill it. Fe double prime will be equal to how much? It will be based on Fe prime minus how much? Minus 1.85 divided by 1.43 and Ca. Sorry, Ca prime, right? Ca prime. Fe prime would be Fe in whichever mineral will come in for projection. Fe prime minus 1.85 by 1.43 Ca prime. So this prime is the same as Fe from here, and minus, what will be this value? 1.294. 1.294, and Ca prime here is equal to Ca minus 0.538 sodium. You see, this is double prime, this is the earlier single prime, and this is going back to the original composition. So now what we will have is, so the equation for Fe prime will be equal to Fe minus 1.294 Ca minus plus minus into minus plus is 0.696. Sorry. This is what is F prime. What is F prime? Is equal to Fe, this Fe, minus 1.294 Ca plus 0.696 sodium. This is the plotting coordinate of Fe prime. And if you look at Mg double prime, it will be the same, because it is Mg prime minus, now you see, 1.85 divided by 1.43 Ca prime. And this is equal to, again, Mg prime is the same as Mg. So you have Mg minus 1.294 again, 1.294 into CA prime. What is CA prime? CA minus 0.538 sodium. And if you do this, then you go back to the same equation. It is Mg minus 1.294 Ca plus 0.696 sodium. So, this is Fe double prime in terms of Fe prime, and this one is in terms of the original Fe. Right? Now we look at aluminium. That's interesting. Now, aluminium double prime is equal to how much? Again, like before, it's aluminium prime minus what? Minus 1.862 divided by 1.43, and this should be Ca prime. If you do that, then Al prime now is this. Al minus 2.077 Na. That's Al prime. Minus, what is the number here?
1.294. Oh no, sorry, 1.302.
1.302. 1.302 into Ca prime, and Ca prime is Ca minus 0.538 Na. Right? So this is Ca prime. No, there is something I missed.
No, sir, it's fine.
No, I missed some. Are we doing correct?
Yes, sir.
Okay. Okay. So here it is now Al minus 2.077 Na minus 1.302 Ca plus 1.302 into 0.538 Na. This is what it is. Have you understood? And so this one will be equal to Al minus 1.302 Ca minus 1.377 Na. This is your Al double prime in terms of Al minus this 1.377. This is this term minus plus of this term. And then you have 1.377 Na. So this is the conversion. So I will erase this now. Where is the place to do it? So I will just erase this since you already have it on your video. You can cross check it. So now for Hornblende of the composition given, Ca double prime will be equal to, I will just write it once, no, not Ca double prime, Al double prime is equal to Al minus 1.302 Ca minus 1.377 Na. Fe double prime is equal to Fe minus 1.294 Ca plus 0.696 Na, and similarly Mg double prime will be equal to Mg minus 1.294 Ca plus 0.696 MA. So this is your second plotting coordinate. So now we went from here to here, projecting from plagioclase. We went from here to here, projecting from this hornblende, but not this hornblende. The modified composition of the hornblende. Why modified? Because already the composition of this hornblende has been projected from the plagioclase. So the composition of plagioclase will not be identical. It will be modified. So that we have to do to calculate L2 prime, from L prime to L2 prime. And then finally we can all go to this. So this is the plotting coordinate that was used. Now you take any mineral and you take its actual value, like I showed it for hornblende. You know, here it's 1.7, so I subtracted it. So you take any mineral, you have this composition. If you have the plagioclase and if you have the hornblende, then you can find out what is the plotting coordinates of this hornblende. What should be? So your phase diagram now includes a triangle where this is Al minus 1.302 Ca minus 1.377 Na, and this one is Fe minus 1.294 Ca plus 0.696 Na, and here it is Mg minus 1.294 Ca plus 0.696 Na. Now you can take a mineral and plot. After converting it this way, you can plot it into this composition space, which is easier now to identify. So that is important. This is what is important. Right? So this is what happens when you project it twice or thrice you may need to project. I have not seen it more than twice. So what happens? The phase assemblages and the phase compositions, like here you saw, the composition of the hornblende become completely distorted. You will not be able to recognize that composition of the hornblende. So what will happen when you're projecting? The minerals compositions will become modified in a new composition space. But so long you keep the variance constant, you're thermodynamically correct. So this is like AFM projection diagram. This is Al double prime, this is Fe double prime, and this is Mg double prime. So you could write Al double prime, Mg double prime, Fe double prime, or these are the plotting coordinates. So if you have a chloride, for example, you can plot and see where they cross. So this is how repeated projections happen. You must remember one thing: if you hold rule 1 to 4 constant, it helps reduce the composition space to a much smaller composition, and you still might land up into 5 or 6 components. So 5 and 6 component space cannot be shown on a piece of paper. So what you do is reduce it. Once you want to reduce it, then you have to plot it from the composition of a phase, which is always part of the assemblages that you want to plot. It should be a part of the assembly. It is not that plagioclase is a part of here or plagioclase is not a part of there. If plagioclase is not there, plagioclase 35 is not there, you can't project it. If there is no plagioclase or a plagioclase of very different composition, you can't project it from a plagioclase type 35. So sometimes when you're working with assemblages, you don't take the exact value, but if the compositional variation is not very big, then you take an average value to plot your coordinates. Similarly for the hornblende. So remember, in a projected diagram, the composition of the mineral will have no similarity with its original composition. It will not have. It cannot have, because its composition is distorted in a distorted space. Just like if you have a torch and put it on my head, when you see the shadow is distorted. If I change the angle, it will be even further distorted. So that's the truth. Okay, I think I will stop here. I will continue with the next video lectures, and then I will let you know. Thank you.